All right, so this leads us into section 10, so linear regression, so, and finding relationships, okay? And so I'll send out this collab to the chat. And this is kind of our introduction to like using modeling to basically make predictions. And to be honest, most people kind of look at linear regression as kind of like an old thing, being like we don't need to do linear regression. We have advanced machine learning models now. But linear regression can actually be very useful to help us give us a quick insight. It's kind of like our quick first tool to go into it. So that's one of the reasons why we talk about it. And that's actually what you'll be using for your project one, mod one, project one, using linear regression. Okay, but the first thing I kind of want to talk about is covariance. So this kind of helps us lead us into like how we analyze our model and see if it works out or not. So covariance, as you might guess, is related to variance, okay? But it actually relates on two variables. So if you remember our variance right here, it measures basically how spread out our data is, or our dispersion from the mean, right? So if you imagine back when we have our nice little bell curve, better bell curve than that, but you get the idea, is that we have the mean right here. Our standard deviation basically is describing how spread out our data is. If we have a bell curve that is very spread out versus a bell curve that is much more pointy, okay, we say this has a lower standard deviation than this one over here. Basically, the values aren't very spread out from the rest of the population. Okay, so covariance allows us to measure basically the relationship between multiple variables. In this case, x and y. Okay, so you can actually see I have this little notation here. So hopefully you guys have seen some before. Basically, you're going through each. This I represents going through each data point. This ij represents going through each data point for the x variable and for the y variable over here. And so these will have different values on here. So you might compare, for example, I think in your project you talk about, price of a house, and maybe the other side would be like, I don't know, the average temperature of the area, okay? And so you see if those relate. And their covariance basically allows you to make that measurement saying how much do they vary from each other. So important term, and that's where it's coming from. And you can see this sigma x sub y is usually how it's written as covariance. Sometimes you will also see as COV. So just know if you'll see COV sometimes as like this variable, it means covariance, okay? And then I think I have a little more information here. Yeah, so here I have positive covariance, okay, and negative covariance, but covariance can range from negative infinity all the way to positive infinity, which actually makes it really difficult to understand when you compare one covariance to another covariance. So for example, if you have like 3 different features and then one, we'll later say call the target, you have this other, basically your effect, and these 3 kind of variables that you can adjust, like x, y, and z. If you find that x and this one match up really well, like a covariance of like 3, and then this variable in your effect matches up with a covariance of like 6.2, it's kind of hard to say, well, exactly how, like which one's really strong by how much, because we have this huge range of what covariance could be. So this actually leads us into correlation. And so again, this will kind of lead to positive covariance and negative covariance. So if something's positively we'll talk about correlation. Positive correlation means that if one value goes up, the other value goes up, they correlate together. And negative covariance basically means that it does the opposite, that as you increase one value, the other value goes down. So we'll see a couple graphs for this. Okay, but this leads us directly into correlation, which is usually what we'll quote when we're talking about models, especially for linear regression. Okay, so this right here is one way to measure correlation. And just know that this guy right here, to be perfectly honest, you don't need to memorize this equation. At least I wouldn't suggest memorizing this equation. When we calculate correlation, we don't usually write out the full formula itself. It might be good practice to understand what's happening in here, but note that we have statistical packages that can do these parts, so we don't have to write this whole equation. But it's good to understand what's going on. And you can see very closely, or very quickly, is that it's very similar to the covariance, at least for Pearson's correlation. You can see we have this top term right here, and then underneath we actually have this square root part, and this is essentially allowing us to normalize how big it is. So this allows us to have a correlation that only ranges from -1 to 1. So now all of a sudden we can have a quick comparison. I was saying, oh, this one's a correlation of 0.83, and this one's a correlation of 0.62. Well, you know, this one is a much higher correlation factor. Like these are much more correlated together versus another one that's a lower value. Okay. And again, what's nice about it too is we get rid of it's independent of units. So it doesn't matter if we're talking about feet, it doesn't matter if we're talking about meters. It doesn't matter what the unit is. It just means that we have a pure correlation number. Cool. All right. Any questions on this so far? I'm kind of going through it pretty quickly, but hopefully it's not feeling too intimidating in that sense. Basically, we're just measuring how things are related to each other. Okay, cool. And stop me, of course, if there's something. So here's a good example of like positive correlation to negative correlation. I believe this is actually from the curriculum. So you'll see this picture again if you go through section 10. And you can see there's this, right, has a positive correlation. Basically, as these values increase, this X part, right, the Y value goes up. We'll call this basically our, we'll talk about in statistical learning, but basically this is your feature and this is your target. Basically, as you increase the target, or as you increase your feature, your target goes up. And you can see like, well, that might not necessarily be true. You know, maybe sometimes it goes up a little higher than normal, than what we'd expect, but it's still really correlated together. Low correlation is like, well, it kind of fluctuates a little bit as we go up, but there's still a general increase. And then no correlation, which is 0, basically means it's random. There's no pattern that we can see that as we increase the feature, something happens to the target. And of course, we have the negative correlation to go basically going in the opposite direction. Note that a negative correlation is probably just as good as having a positive correlation of the same absolute value. It just means that it's going in a different direction of your feature. Basically, you want kind of like the lower the correlation absolute value is, the more you're leaning on lines like, you know, maybe they're not related to each other. Okay, they're not correlated. Cool. All right. So this will lead us into statistical learning. Okay, and statistical learning really is kind of like, you can hear like this learning part. Basically, it allows us to reiterate things to get better and better predictions. Okay, so the first thing I kind of talk about is kind of like the introduction, a little bit of terms. So hopefully you've seen these terms before, but basically your variables are either an independent variable, a dependent variable, and usually people don't really talk about this one, but also there's your controlled variables. And you can kind of say that your independent variable is the thing you are changing, or the thing that is changing and causing an effect. Your dependent variable is dependent, okay, on your independent variables. Your dependent variable, you can think of it as this y. What is the effect that happens? Your controlled variables are things basically that hopefully you kept constant in the sense. So for example, in the study of like looking at first graders and if they like Superman or Batman more, a controlled variable might be that you didn't say, do you like Superman more or Batman? Like, that would be something that you'd have to control, is saying, oh, how do you express this? Again, this is more like scientific testing, but that's where it's coming from. Okay, and we'll talk about a statistical model, and our statistical model really is a function. And later on, we'll actually kind of call this a mapping, because our model can really be a whole bunch of things. But for now, for linear regression, it really is a function. We can write it in math. Basically, we can write this whole thing completely math. Later on, when we do machine learning, it's much more like a mapping where it's not a clear function that's being created, but it defines a relationship. It says, how do these points relate? So you can see here, I have a scatter plot of weight versus height, okay? And I believe this is also from the curriculum too. But basically saying, how does height and weight correlate? In this case, we tend to put the independent variable, and by 10, I mean like almost always, put the independent variable on the x-axis, okay, and the dependent variable on the y-axis. So you can think like cause and effect, right? So as we increase the height, do we increase in weight? And so this probably, like if someone said, I'm like, yeah, that makes sense. If you increase height, you would expect someone to be heavier, right? Like that's just kind of like a general knowledge. But then you kind of think about it for a second, and you're like, but you could be shorter and still be more, be heavier than someone who's taller, right? You can think of someone who's very skinny at 6'5", versus someone who maybe is like, 5'5", but more stout. So you can kind of imagine like, well, there's some variance in there. but we can make a statistical model, we can make a function, right? To basically say, well, you know, as we increase in height, you'll increase in weight. Okay, so that's exactly what this is. And basically, we'll talk about what this is, but this is a regression line, our line of best fit. And basically, we're trying our best to predict on this weight and height relationship. Okay, cool. Any questions on this so far? This is going to be the main meat of like what we do for regression, or sorry, linear regression. Okay, cool. Looks good. Quick thumbs up if you're feeling pretty good so far. We talked about sideways, you're like, I don't quite understand. Thumbs down, being like, this is completely over my head. Okay, that's good. I see some sideways thumbs. That's good. Again, there's a lot more in the curriculum that will go in more detail. I'm going through pretty quickly. But the main thing you should know is that you can have essentially your feature, your target, and how they're related with the correlation. And we're using our statistical model, basically a function, to predict that. And we'll find that it's all linear, meaning aligned. Okay, so I think I finally say here, I probably should move this up. I don't know why I have this so far down, but this right here basically are parameters to build the model, because it is a function. So think of like, what's the equation for a line? Anyone remember? I know someone has it memorized. It's been drilled in your head at some point, right?
mx plus b.
Y equals mx plus b. Yeah, that's the classic, right? So this is basically for linear regression. That's exactly what it is. Y equals mx plus b. You'll see me use ax because I just like being different. No, because the b part just is a little different from it. And later on, we'll see that we can have multiple terms in here. But yeah, y equals mx plus b, you can just think of as a number, right? M being the slope, b being your intercept. Hopefully that feels pretty, hopefully that's not news to you guys. That one's from a basic, just creating a line, okay? So that leads us into a little bit saying, okay, cool, we can make a model and everything like that, okay? But then we say, okay, well, let's say, how do we figure this line out? So one thing we can do is actually something called learning, right? We can kind of essentially keep figuring things out as we, like we keep adjusting it and seeing what does better. So we can do something called model validation, okay? And the curriculum talks about this a little bit, but I kind of want to just say quickly like what model validation is. So validation basically splits the data into training and testing. So essentially we'll try to create the statistical model with the training data, and then we'll test out our model with a testing part of the data. But your data is this huge bunch of stuff, right? So it's not clear what should be your test and what should be your train. So what you do, you randomly split it across, say, well, okay, this much of the data I'm going to use just to train my model. And then this part of the data I'm going to use to test out my model. Okay. So why might we want to actually just put or split into training and testing? Why don't we just use all the data for testing? Anyone got an idea? So I see someone's mic went off. If anyone has
And it's not testing. We need the training set to validate the model.
Good, right. So we do have to validate it. And the best way I kind of think about this is like, imagine if you like are teaching a kid, like a little kid, say, this is a dog, this is a cat, you know? And they're like, dog, cat, dog, cat, dog, cat. And if you ever like talk to little kids when they're first learning, it's actually really fun because they'll say, oh, everything's either a dog or a cat. If you all of a sudden give them a data set, essentially a picture of a cow, and they've never learned what a cow is, they'll say dog, or they'll say cat. And you're like, no, like that's a cow. And they're like, what's a cow? So this is, for example, like why you want to split your training and testing randomly too. If you test on everything, you might overfit essentially. And you also, if you don't test with enough information, you might underfit. In that case, underfitting with the dog and cat, with the cow part, you never saw a cow. So that's why you have to randomly go through it. And there's actual like ways you can make sure to split your training and testing so you can use the most possible amount of testing. Because ideally we would love to have a huge test set, right? But the problem is if we made it like we use that whole test set, that test will also include outliers, and that will affect our model. And we don't want to necessarily include those, we don't want to use the testing part to include outliers because they're by nature outliers, they're not expected. They're way out from the normal kind of deal. So that's why we kind of end up splitting the test and training. And this will be more obvious as we get more into machine learning, like the deeper parts of that. But there are also strategies like k-fold, you know, validation. So just know that's why we do validation. And the way we test to say, okay, we can do a training and we can test. How do we test? Well, the training basically will be to create this line, this model. Our testing, we use something called a loss function. And our loss function basically allows us to say, okay, well, how good is our line? How good is our model? And this loss function, we'll talk about what this is in linear regression, but our loss function is the thing that kind of says, well, how good is it? And this can be different depending on what algorithm or what kind of model you're using. In the case of linear regression, we'll actually use something called RSS. Basically our residuals, basically how different our points are from our line. But in other models, we might use a different kind of loss function, especially as we get into more advanced machine learning techniques. Okay, cool. So again, this is kind of like going all into ready to do linear regression. And so I'm going to get into this in a second, but I just wanted to say linear regression, we're going to do simple linear regression, which basically means one feature, one target. With section 11, which we'll talk about next week, it'll be multiple features, right? And by multiple, it could literally be like 20, 30, even 100 or whatever many features to make one model for one target. Basically all these features, how they change to change one target part. So that's kind of what we're getting into. So I kind of said a bunch for already, but linear regression, basically, you have a bunch of data, right? In this case, it doesn't really matter what this data is, it's not labeled, right? But we have a bunch of data points. You can think of like a scatter plot, and your regression line is your line that best predicts that data. Now note, however, that most of the data points are likely not to be on that line, right? Or you might even be pretty far away from that line. And that's because your data has some random noise into it, right? But the goal is basically say, well, if our data has a general pattern, we can create a linear regression line to help predict that information, okay? And we'll explore basically like how we actually would do that. So again, this was the motivation for why we do it. And I said at the beginning, it's a data science go-to. Like it's a very quick way to do a model. Note there are limitations. So for example, as we get, well, first of all, we'll talk about when is it good, but a linear regression model isn't very good for certain sets of data. And also when we start getting to very large number of features, it turns out that system of equations that we have to try to figure out this like hyperdimensional plane turns out to be very difficult to computationally expensive. And so that's one of the motivations of why we end up doing other techniques. Like, well, if we're going to use all this computation to do stuff anyway, maybe we can do another algorithm that can explain the data better. So that's kind of like where we're going towards. But linear regression has been around for a long time. You can talk to most statisticians, and that's like their bread and butter of like their go-to first. And to be honest, a lot of data scientists right now will try to skip over this, but it's always a good thing to do because usually it doesn't take too much time compared to a machine learning, deep learning, like neural network. But it can give you a lot of insight, at least say, hey, if you can predict it really well with linear regression, you might not even need to do a advanced machine learning model. Or if you do need to do that, at least you have the result to do some basic testing on it. So for example, if you're talking to your boss and your boss is like, hey, we need to get this stuff. We have a deadline for this. We need a prediction kind of thing. If you do a linear regression, you find out, oh, it predicts like 85% of the results. That might be good enough for what you guys need at that moment versus waiting for like 4 days when you're trying to figure out how to train the best way to train it from a more advanced machine learning technique. So that's kind of the motivation of what's going on. And it's a great introduction to our first real model set. Okay, so we'll get into right now that, good, oh, good. I was worried I was not gonna have enough time, but I think we're gonna be good. So creating a linear regression line, okay. And again, this is a lot going on here. This is in the curriculum, so don't feel like you have to absorb it all right now. In fact, this exact picture is from the curriculum. So it's basically our line of best fit, right? You'll hear this a lot, regression line of best fit. And that basically is saying our Y, which is our target, our X is our feature, and our A is basically our slope of the line, and B is our Y-intercept, okay? And so basically this is like all regression lines, well, simple regression lines will be in this form, okay? And the way we find the slope actually is really nice is that all we have to do is basically find the correlation factor, okay, which we saw how to calculate earlier with Pearson's correlation, okay? And SY and SX are the sample standard deviations. So basically the standard deviations of the sample. So basically how much does Y vary and how much does the X variable vary? And this basically will give us right here our regression line. So it's a very quick, easy way to kind of like, okay, cool. We can just use this part and figure out a regression line very quickly, okay? And so this right here is kind of showing a little bit of all the parts. So pretty much if you were to like, if someone were to say to you like in a job interview and say, explain to me linear regression lines, if you drew out this picture and then explained each part, you would pretty much hit everything, nearly everything you would need to know about linear regression. And then they'd say, okay, cool, let's move on to the next question. So this blue line right here is our linear regression line, our line of best fit. Our green squares are our data points themselves, okay? This right here is just saying it's the slope, right? It's just saying, okay, the change in X, rise over run for slope. Hopefully you guys feel pretty comfortable with that. And then what comes down to is like, okay, how do we know? Oh, and of course we have our y-intercept here. Note that we write it, that they wrote in this picture right here, y equals w0 plus w1x. And this actually comes from the fact that later on, as we expand this out, we can actually have multiple ones. So later on we'll have, oh, real quick, y hat is our prediction. It's not the actual y. That's why we have y hat. Y hat w0, which is our y-intercept. Also, we called it b earlier. w1 times x1, right? And w1 is our slope, right? Our m, or in this case, sometimes I'll write it as a. But we can also have later on, we're going to get this next time, but w2, x2, and we can have multiple features and go on and on like that. So this is kind of the reason why there's a 0 and 1 versus keeping it mx plus b, okay? So, but anyway, we have our linear regression line, and we'll talk about how we even get that linear regression line, but let's say we have it, and we want to test it against these data points. And so with these data points, these green squares, we can say how far away is it from the regression line. So essentially we can say, okay, how far away is it? In this case, y hat is our prediction, which is this point right here. You say how far up y hat, and then minus y, which is this guy, how far is. Basically we're saying this equation right here is saying how far away is it from the line, okay? And we'll see that we'll actually use that value, say like how far is it from here, and we'll actually square it in a second. And this will help give us a value, and we'll add these all up. So, okay, let's move this out of the way. Trying to move my hands. There we go, okay. So you're like, okay, cool. That's how we would use a linear regression. That's how we can kind of predict it, right? But there's a few subtle things. So one thing is, how good is our linear regression line, okay? And it turns out there's a little bit of a subtle point. So like I said, is that you can use how far away that point is from the line. This is called the residual, okay? Basically how far it resides from the line itself. And we can actually add up the sum of all of these distances. So the sum of squares, usually here that's sum of squares. In fact, we can do the residual sum of squares, our RSS, sorry, too many S's. So anyway, we can figure this out. And this is essentially what we'll usually use to describe what this part is, like kind of like our function. Now, normally though, when we actually report our linear regression line, we'll actually use something called R squared, right? This, I don't usually see it as this RSQ. Usually you'll see it as this R squared like this, okay? And this is basically telling us very quickly, like we'll do stats models in section 10 when you proceed with all that, and you'll actually see the factor they'll spit out is your R squared value. Okay, and this kind of gives us a quick judgment saying how good is our model explaining our data. Okay, so it's actually, if you look at this equation, and again, don't feel like you have to memorize this equation because there's a lot going on here, but basically what's really happening is that this equation tells us R squared is saying how good is our model, and our model's up here, this yi minus y prediction, right? This y hat. That's our prediction part. Basically, how far is this residual going on here? Divided by the same thing, but you'll notice it has the y bar. Y bar is our mean, the mean of the data. And what it really means, it's basically R squared is saying how good is our prediction compared to if we just were really, really lazy and said everything was the mean. Basically, if you drew a straight line and said, okay, what's the mean of this value? Like, let's say like for height versus weight. and say, what's the mean weight? And you said, oh, the mean weight is, I don't know, 200 pounds, okay? And 200 pounds, and you just drew a straight line and said, okay, whenever someone says how tall they are, we just say they're 200 pounds. That's kind of like your worst model. Essentially, you're just saying, all right, we're using one value to get it versus like actually trying to build a relationship. And it says, okay, let's use that model as our worst possible model. That's what this bottom part is. And then let's use our line of best fit or a potential line of best fit. And we use that to say how far away those points are. And we compare those two parts and see how good they are. So this basically will actually range from 1 to 0. So the closer you are to 1, the better your model is. Okay, and really what this value is saying, usually you hear percentage and stuff like that. It explains how to, I'm gonna make sure I get this. Okay. I'll hear people explain this in different ways. And I think the most correct way of saying this, so if this gives me out like an R-squared value of 0.85, you'll usually hear people say, oh, our model explains 85% of the data points. That's not quite true in the way it's phrased. It's not that it's explaining 85% of our data points. What it's really doing, it's saying it's explaining 85% of the variations from our worst model. So it's really explaining 85% of the variation from this part right here. So you can kind of imagine is that if we had an R-squared value of 1 kind of deal, it's a perfect model. That means every point is lying on the line, right? So our model explains 100% of the variations from the data. If we had some points that were slightly off our linear regression line, then our R-squared value will be slightly less than 1, let's say 0.9. So only 99% is explained by our model. And that's really what our R-squared factor is talking about, is saying how much of the variations from our data is actually explained by our model, because you always have slight variations from it. Okay. And so you can kind of see right here is that here's another example. And first of all, just looking at this, what do you guys think? Is this a good model, bad model? Or do you think it explains the data well? Any comments on that?
It's an okay-ish model.
Okay, yeah. Dave said okay-ish. I saw Bonnie go like this, okay? And would someone like to share like why it might be an okay-ish? Like what do you guys notice that doesn't quite look right? Or that would make you think it's an okay-ish model?
Well, I know that generally, well, 0.85 is actually pretty good.
Yeah, it might be pretty good.
General.
Yeah, you can see it like right here.
Yeah, but there are some outliers.
Yeah, there's definitely something that's kind of not quite matching. Like for example, this stuff down here, maybe even the stuff up here, but you'll notice that it kind of goes outward, right? You kind of say, oh, you're going up and it kind of expands out. You can kind of look, if I ignored this red line and I drew like kind of like its boundary, you'll see it kind of looks more like a cone shape. And so this is where it's like, you know, our model technically works, but if you imagine now, let's say we stop collecting data at TV 300, whatever this model is, right? But later on, we find out that our data actually comes out much higher than that. Maybe, for example, our data points go all the way to like 500 in like a real world situation. And so like we have like points over here. We might expect our model to get worse and worse and worse. And one of the reasons why, the key here is to realize our model doesn't actually follow a nice line curve. It kind of follows more like this kind of cone shape kind of going on here. So maybe our model is not best explained by a linear model. And that kind of leads us into when does a linear regression line work? Okay. So the main thing, and I'm going to go through this relatively quickly, it has more in your curriculum, so in case we kind of run a little bit out of time. But our linear regression line works basically when it's linear. When we have a linear relationship, our linear regression works. Okay, so that includes for positive correlation, negative correlation, but you'll notice like here, right, we have much more like a logarithmic kind of or exponential curve going on here. Maybe it's parabolic or something. We could at first draw a line through here, but eventually our model might not explain it very well. So this is the stuff you have to be careful with. And this is actually why scatter plots are really important instead of just, because you can run a regression analysis without ever plotting anything. And you might get an R-squared value, but find out it's like, ooh, this was no good. So this is actually a good reason why you should put out scatter plots. I might have said this before, but I'll say it again, is humans are really good at detecting visual patterns. Like for whatever reason, evolutionarily wise, we have a really good job of like finding patterns, sometimes when there's no pattern to be found. but it can help us guide us into figuring out, saying, maybe I should investigate this further. It's not going to give you, like, let me be honest, is that your intuition as a person is never going to be perfectly accurate. In fact, it'll probably be flawed at points, but it can help you identify patterns when you actually visually put them out there. You can very quickly see, oh, like when you look at this, you can very quickly say, oh, that model is not going to work as well because that data is just not linear. Okay? And that's something that is a little harder to express, because really when you do statistics, we're really trying to get a summary of our data, and it's just hard to do that. Okay. So anyway, linear regression has to have a linear relationship to do well. Okay. You might be able to get decently like this, but then really you should be using a different model if it's not linear. Okay. The next part is that it should be normal distribution. Now, technically, you don't actually need it to be normal to do a linear regression line. It just really helps in the basically analysis, especially for z-testing. So just kind of know is that, okay, like we like it to be normal, but you could do a linear regression line even if it's not normally spread out. And that kind of does some interesting things, like if you have more skewness in it and stuff like that. But the main reason is you have z-test and allowing us to do a confidence interval, saying how good is our R-squared value, how good is our regression line with confidence. And again, there's more detail in the curriculum itself. But there's two ways we can see how good something normal is. One is basically doing, what's it called, a histogram. So you can see our histogram right here, and we can see like, oh, that's approximately normal. Here it's a little too peaked in the middle. This one's actually not heteroscedasticity. Our, blanking on the name, guys, kurtosis, right? Basically very peaked up here. We talked about that from last time. So this is like a really peaked one. And then of course we have skew data where it's no longer normally distributed. On the side here, this again comes from the curriculum itself. You can see our Q plots, our QQ plots. And this basically is describing the same thing, but more in a line form. So in a line, this would mean that's in a normal distribution. And then as we get away from a normal distribution, you'll actually see a different shape on this line. Again, the curriculum goes into more detail on this, but these are just quick ways to basically analyze, saying, hey, is it a normal distribution? Does it make sense for us to be able to do a z-test? Okay. And if it's not like that, then we have to figure out a different way to approach this, or we can transform our data, which we'll talk about in section 12. We can transform our data to actually make it more normal, or make it more into that direction of what would be easier to do a test on. Okay, cool. Again, just a way to visualize it. And then lastly, this brings us to I can never say this word, heteroscedasticity, or heterodiscedasticity, all right? Which basically is saying how much, how are the like errors or residuals really, basically how far are the residuals spread out. So if a residual is spread out, like change in position over time, then it might mean that there might be some other thing going on. So for example, you might see that the residuals over here start getting very large compared to very small residuals over here, which might suggest, hey, this is not the right model to use. You need to use something that's not a linear regression, or transform the data to make it more linear. Okay, so that's what this part is. And you can actually use these plots. Note that these points are plotting out the residuals, not the actual data. So it's not the data itself, it's just saying how far those data points vary from the linear regression line. And you can see here, we have it mostly randomly scattered. Residuals kind of go negative, positive. There's not a clear pattern here. Versus here, we clearly see that it varies a lot. That might be like close to like what we saw in our first model. And here we can see something very similar where we actually get very negative residuals at the beginning, then positive residuals, and then negative again. And this suggests this might mean that there's some other, other model that would explain this better. And in this notebook, I actually put in a little explanation, little link to a different explanation that goes into quite a bit of detail about heteroscedasticity. But I thought it was a really good one to kind of explain like what you're looking for when you're looking to see if it's worth, if you're got a good data set to actually model against. Okay, cool. All right, guys. So that kind of ends me for here. Kind of hitting a little later than I would have normally liked, but you guys have any questions? Okay, cool. Thumbs up, thumbs down, sideways. How you feeling on this? Cool. I see some thumbs up on there. Some sideways. That's fine. No, don't feel bad if you have a sideways thumb. There's a lot to go through. If you had exposure to this before, it might be easier to digest, but always going into more detail always helps.
Can you just remind us the difference between the hetero and the homo again?
Yeah, so you're talking about heteroscedasticity here, right?
Cool. Yeah.
Okay. Yeah, so the main thing is that basically how much your residuals differ from your regression line, from your model, I should say. So this one right here, we can see each point is the actual residuals. And as we vary across from like along the independent variable. So for example, I'll kind of show this plot up here because this explains a lot. So right here, we actually have, like, if I drew this out, I'll use green. We have a very large residuals, and then it gets very small. So you can see like the residuals are very, very small, and then they start getting bigger. In fact, when we start getting really out here, we can actually see the residuals get quite large. Okay, so what this would kind of look like is like if I drew a graph on top of here saying, okay, let me say, how did the residuals work? So this is a positive residual, a negative residual, right? You might see something where, okay, like it starts off some positive, some negative, but then as we get further away, like towards the 300 range, we can actually see the residuals get very, very large. I don't know how well you guys can see those points, but our residuals are kind of getting much further away. And so we'd actually have that heteroscedasticity there. If our model instead was looking something like a line like this, and we have our points kind of scattered more or less along the line, but you can see like it doesn't vary very much, like how much it changes from the line. This would be homo. So this would be your residuals are essentially the same, like the same spread of residuals throughout the whole time. And that's what you'd want. You want something that's basically kind of random, essentially randomly scattered versus an actual pattern. That makes sense?
Okay, so hetero, the residuals start to spiral and get larger as the numbers get bigger. The homoscedasticity, the residual sort of remains sort of constant.
Right, yeah, at least like there's not a direct pattern. So that's the big thing, is that there's not a pattern in there versus something that's definitely got a pattern in it. So for example, well, I guess that is hetero. Sorry, I can't talk anymore. Heteroscedasticity is when we do have that change over time versus homo, meaning that it hasn't changed that much. It's consistent. But also, this is not like any specific hetero versus homo hedascity, right? But this is not good either. We don't want this. We want something that is more consistent, basically random across our line, our model. Okay. Does that answer your question?
So the homoscedasticity was like almost like parallel lines, and hetero seems to have some sort of pattern. And we prefer homoscedasticity because it does what again? There's less.
Basically suggesting that there's some pattern here that we're not accounting for. And that's why when we have a pattern like this heteroscedasticity, there's some pattern in there that we're not accounting for, which means that we need to investigate further, saying, hey, why is our model getting worse, or in this case better, as we go further and further out? Like that might mean that we might need to suggest a new model. For example, this nonlinear part, you might, for example, say, oh, this is actually a parabola, or there might be some other like function that we didn't account for. This is just another way to observe it.
Okay, so the heteroscedasticity, homoscedasticity could be thought of as a test of the model to see just how well the model explains the data points. And if it's too hetero, that's like, oh, dang, there's something we didn't take into account for. Gotta go check again. Homo, oh, yay. Looks like everything's in order. This model is good. Let's move on.
That's right. Yeah, I think that's the general idea. And again, this is where like these things, like it's kind of subjective. There's not like a direct like, oh, when it's this thing, it's 100%, we need to throw out our model, or, oh, it's completely fine. You'll notice like there's these lines here. You usually won't see this kind of spread. It's going to be a lot fuzzier and being like, does it make sense? And subjective in that sense of being like, well, if it's slightly heteroscedastic, you might be okay with that. Being like, well, our data, we'd expect this kind of thing. But we're not expecting very large values to go out. So maybe it's fine that's a slightly not homo, like homoscedastic.
Okay.
Cool. All right, good question. All right, guys. Any other questions? I know we're kind of over, but if you guys want to ask anything else, now would be a good time.